Let's start with question number 19. Now the question you see here belongs to a section of mechanics. Now here a long cylindrical vessel is half filled with liquid. When the vessel is rotated about its own axis with a speed, let's take omega, the liquid rises up near the wall. If the radius of the vessel is 5 centimeter and its rotational speed is 2 rotations per second, that's the omega we have right now, then the difference of heights between the center and the sides in centimeter will be. So let's see the diagram first. In order to understand this, we need to know the diagram, right? So let's take this be the container, right? And it was rotating about its central axis in this manner, right? So the liquid which was normally like this, it moved up to this shape due to this angular rotation. What we want is, what is the value of this y if this is the value of x, and this is basically the radius, right? So at any point of time, let's see here, it will make some angle, that is theta with the horizontal. Now you are well aware, in that situation tan theta would be equal to omega square x by g, right? You also know at this point of time tan theta can also be written as dy by dx, that is equals to omega square x by g, right? So this won't be solved by geometry because it does not hold a direct relation, it's a curvilinear path. So I'll say dy would be equal to omega square x dx by g. Let's integrate this from 0 to y, and this as a radius is given to us as 5 centimeter. That means the radius value, that is 5 into 10 to power minus 2. Putting this value 5 into 10 to power minus 2, you will get y is equals to omega square by g, which would be commonly outside, into x square by 2 and 0 to 5 into 10 to power minus 2. Putting the values and solving it, you will get y equals to 1.9 centimeter. Let's see which is the closest option. So as far as the question is concerned, among the 4, option number 4 would be the right answer, right? Let's move ahead and solve our next question. Now in here you see this is the plano-convex lens, belongs to section optics, and the plano-convex lens has focal length f2 and refractive index mu2, radius of curvature being r. And it fits with a plano-concave lens of refractive index mu1, focal length f1 and radius of curvature r again. That means curvatures are same. The plane surfaces are parallel to each other. Then the focal length of combination will be, let's see which is the best option here. Before we proceed with the solution, let's have the diagram first. So this would be the case, right? Now here it's something like this, where this is mu2, this is mu1, this is the plano-convex and this would be the plano-concave. Radius of curvature for both is same. For this focal length is f2 and for this focal length is f1, right? On simple note, we are well aware for such situations, that is focal length f2 can be written as mu2 minus 1 by r, and for focal length f1, since it's a concave, so I will say minus of mu1 minus 1 by r, right? Now when you add these two, simply it's a combination of lengths, so the net focal length, when you say net power, will be equal to p1 plus p2, or 1 upon focal length would be simply equal to 1 upon f1 plus 1 upon f2. Let's put down the values. Minus of mu1 minus 1 by r plus mu2 minus 1 by r. So 1 by f, and thus you will find 1 by f is equals to mu2 minus mu1 by r, or I'll say f is equals to r by mu2 minus mu1. Let's see which is the best suited option here. So among the 4 given cases, option number 2 would be the right answer, right? Let's move ahead and solve our next question. The question you see here belongs to a section of modern physics. In this question, the Frank-Hertz experiment, an electron of energy 5.6 electron volts passes through a mercury vapor and emerges with energy of 0.7 electron volt. So that is, the difference has been lost, which is nearly 4.9 volts. Now, the minimum wavelength of photons emitted by mercury atom is close to. It's very simple question. Let's start with the solution. So what is the energy which is lost? Delta E, that should be equal to 5.6 minus 0.7 electron volt, that would be 5.9 electron volt, and this energy will be simply hc by lambda, lambda of the wavelength of the photons which has been emitted. Solving this, you will get lambda is equals to hc by 4.9 electron volts, and this will be close to 250 nanometers, right? Let's see which is the best suited option here. Among the given options, option number 3 would be the right answer. Let's move ahead and solve our next question, that is question number 22.